problem that we want to solve this week is as follows. We're given a rectangle with sides A and B, where A is greater than B, so A is the longer side, and we're being asked to fold it along the diagonal so that this lower rectangle gets folded up over the upper rectangle like this. So here is the upper rectangle, here, and here's the lower rectangle that got folded up and over like this. And we're being asked to determine the area of the overlapping triangle, the intersection of these two larger triangles here. So we're being asked to calculate this shaded area. My first thought is that the problem says to fold a rectangle along the diagonal. Well, if I have a sheet of paper, I could fold that along the diagonal. Now, usually a typing paper or a loose leaf paper is a little bit big, and if I want to go to the opposite corners, it's a long way off, and it becomes a more manageable problem if I just first fold my paper in half and make a smaller rectangle. And there, now I can play with that. And I can do what the problem said, and I can fold along the diagonal, and this lower triangle will come up over this upper triangle like this, just like in the diagram. Just like in the diagram in the problem. And I drew in these lines so that I could see better. And where those lines come from, I see how this lower long edge comes up and over this upper long edge so that the lower edge and the upper edge intersect at this point of intersection here. And so when I draw in this line segment from the point of intersection to this vertex here, that gives me a line segment that lies along the original upper edge of the original rectangle. And similarly, if I draw a line segment from this point of intersection to this corner, then I get this line segment which lies along this long edge, which originally came from my rectangle. And the resulting triangle from this line segment and this line segment and this folded edge is that the triangle that we're trying to calculate the area of. So that's easy to see. And the original side lengths were B for the short sides, there, and A for the long sides, there, and there. The second thing I notice about this problem is all the right triangles in it. So even before I folded this rectangle, by making this diagonal, I have cut the rectangle into two equal halves. Each one of these is a right triangle with side lengths A and B, legs A and B, and they share the same hypotenuse, namely this diagonal. So these are two right triangles here. And when I fold this lower triangle up over the upper triangle, I notice that I form two more smaller right triangles right on the side here, with this right angle that came from the corner of the rectangle. This corner of the rectangle came up here and became this corner of this new smaller right triangle, and this new smaller right triangle here. And this corner is from this upper left corner of my original rectangle. So a lot of right triangles going on in this picture, which makes me think immediately of the Pythagorean Theorem. So I think that this problem is going to involve the Pythagorean Theorem somehow. And so let's go ahead and recall how that goes. So I'll write it down. And let's recall that if I have a right triangle with legs A and B and hypotenuse C, then the Pythagorean theorem says that the sum of squares of the legs is equal to the square of the hypotenuse. And because of all the right triangles in this problem, immediately, before I even start solving the problem, I suspect immediately that I'm going to have to use this theorem. The third thing I notice about this problem is the symmetry. Now we formed this triangle by first taking a rectangle and splitting it into two equal halves so that these two right triangles are congruent, each having legs A and B and sharing the same hypotenuse. And so in particular, this small angle here opposite B is congruent to this small angle here opposite this side length B, so that when I fold them over, this small angle here opposite B is the same as this small angle here opposite B in this right triangle. So I know these angles are the same. Like this. And that means that the triangle that we've made is an isosceles triangle. And that means that the sides opposite the equal angles have to be the same. So this length is equal to this length. I'm going to call it x, like this. Another way to prove that this side length x is equal to this side length x is to look at these vertically opposite angles here. I'm going to call them beta. So vertically opposite angles are congruent. And the side opposite beta in this right triangle is B. And the side opposite beta in this right triangle is also B. And since a right triangle is completely determined given any one side and one of its complementary angles, that means that these two smaller right triangles are congruent, which means that the hypotenuse of each is the same length. And so that's another way to show that this is an isosceles triangle. Now remembering that this longer edge of my original rectangle is of length A, that when I flipped this triangle up over and I found this is, I'm calling it x, what's left over here is what's left after you take x away from A, and same over here. So this is A minus x, whatever x is. Now, the next thing that I want to do is consider each of my options for calculating the area of this isosceles triangle. Because if I consider each option, then I can choose the best one. Now I see three approaches to calculating the area of this isosceles triangle. The first thing that jumps to mind is that I can look at this big right triangle here, which has legs length A and B, and I could subtract the smaller right triangle here, and that would give me what would remain, would be the triangle I seek. So what is the area of the larger right triangle? It's 1/2 of its base b times its height a, so 1/2 of AB, and then subtract the smaller rectangle, which is 1/2 of its base times its height, and so that would be 1/2 of this base times this height. I'm getting 1/2 of a minus x times b, like that. And in order to calculate this quantity, I need to know this side length x right here. So that's my first option. The second approach that I could take to calculate the area of this triangle would be to use the folded edge for the base, and then I could drop a perpendicular from this vertex to get the height. Now I know that this folded edge came from the hypotenuse of this right triangle with legs a and b, so I know that the folded edge is the square root of a squared plus b squared from the Pythagorean theorem. So I know the base of this triangle is the square root of a squared plus b squared. And then I would need to know the height, and then the area of this triangle would be 1/2 of its base times its height, like that. So this is a second method for calculating this area. Now, in order to accomplish that, I would need to be able to calculate h. Now, I can do that because I know that this is a perpendicular bisector for this isosceles triangle, which will cut this into two equal right triangles with hypotenuse x and angle alpha, and this side length would be the same as this side length, would be 1/2 of the square root of a squared plus b squared on each side, like that. So I could do it. I could calculate h from the Pythagorean theorem if I knew x, because I know a and b, those are given. So in order to use this strategy to calculate the area of this isosceles triangle, I would need to know h. But in order to be able to get h, I would need to know x. So this strategy is taking more steps than this one, because this is more direct, because this strategy requires me to just get x. But this strategy requires me to get h, which in turn requires me to know x. So in either case I need to know x, but this is faster, because this one I won't have to calculate h. The final strategy that I can think of to try to calculate this area is to use one of the other edges of this triangle for the base. And just for fun, I'm going to pretend like I didn't know that these two side lengths are equal, just for a moment. And I'm going to show you something kind of neat. So, okay, strategy. Let's go ahead and turn this around. And use this edge as a base for my triangle. And what's the height? Well, here I can see that I've dropped a perpendicular from this vertex of the triangle to the base, so the height is this value, b. And so what I have is that the area of this triangle is 1/2 the base times the height, so 1/2 this base y times the height of b. So there we go. On the other hand, using this side as a base instead, we've got the same thing. We have that the area of this triangle is 1/2 its base times the height, b, which I found from dropping the perpendicular from this vertex down to the base. And so that's 1/2, base times height is 1/2 of x times the height, which is b. And so the cool thing that this strategy gave us is that because I know that the area of this triangle is equal to this, and it's also equal to this, that means that x does equal y, which we already figured out before. But if you hadn't noticed the symmetry of this problem, then trying this strategy by using the other edges for the base, you would get x equals y for free without having to consider congruent triangles or congruent angles or anything. But just from knowing that this is two different ways of expressing the same area, and so this equation tells us that x must equal y when we divide out the b and multiply both sides by 2. So now I'm evaluating all three of my options for calculating the area of my triangle. Here they are. And each one of these options, no matter which one I choose, I end up having to calculate that value x. In order to get h, I require the value for x. This option looks the shortest and the fastest, just 1/2 x times b. This option is actually the same. If you look at the algebra, this will simplify down to exactly that, because this minus sign, and when I multiply 1/2 ab, will subtract from the 1/2 ab, and these two minuses will make a plus, and I will be left with a positive 1/2 xb, which is the same as this formula here. So these are actually equivalent, but this is more direct because I didn't even need to simplify this algebra down at all, but I was able to write the formula down directly. So this is the optimal method, I think, that I'm going to use, and I need to calculate x. So I'm going to show how I do that next. So I'm going to look at my triangle. So I need to figure out how to calculate x in order to calculate this area here. Well, I noticed that in this small right triangle here, it shows how to relate the unknown quantity x to each of the two known quantities a and b. And the Pythagorean theorem will give us one equation which will contain the one unknown x, so I'll be able to solve for it. And I can do that like this. So I need to take the sum of the squares of the legs and set it equal to the square of the hypotenuse, like this. So this leg is a minus x, so I'm going to square that leg, plus this leg is b, so I'm going to square that leg, and set that sum equal to the square of the hypotenuse. One equation and one unknown x. So I can solve for x. And what I'm going to do is I'm going to multiply this square out. So a minus x squared is a squared minus 2ax plus x squared. And then here's the term b squared, I'm going to write that down, equals x squared. And then I notice what happens is that I have the quantity x squared on both sides. So I can subtract x squared from both sides, and I can add 2ax to both sides, and I'm solving for x. So 2ax equals a squared plus b squared. And so I see that x, the quantity I wanted, is equal to a squared plus b squared over 2a. And so now I'm done, because remember, the area of this rectangle was 1/2 the base times the height. And the base was x, and the height was b, so 1/2 of xb, but I know what x is now. It's a squared plus b squared over 2a, so plugging x into the formula, it gives me 1/2 of x times b, and x is a squared plus b squared over 2a. And I found the area. This can simplify if you like. It becomes b over 4a times a squared plus b squared. And the problem is solved. And since the length a was given to be longer than b, this is a fraction which is less than 1. So the area of my isosceles triangle is a quantity that is less than a squared plus b squared. And in the case when a equals b, where you have a square rather than a rectangle, this formula will become b over a will be 1, and you'll have 1/4 of a squared plus b squared, but b squared will be a squared because a is b, and so we will get 1/2 of a squared, which makes sense because the square will be side length a, and the area of the square will be a squared, and the triangle we'll get will be half of the square. If you cut the square down the diagonal, it will be exactly halfway. And that will be half of the square, which is 1/2 a squared. So this formula agrees with the case when your rectangle is a square. And the problem is solved. And this is the answer in the general case. Now just one more thing. We don't have to do this, but I thought it would be instructive if we considered what happens if we use this method instead. Remember, this is the method that we thought this is the long way around, we won't do it. But what happens if we do use this method? We've come this far, so why not? And it will also serve as a way to check our answer that we got using this method. So here's what my alternative solution looks like. So I'm going to calculate this area by using 1/2 of the base times the height, but I need to know what is the height, and in order to calculate this h, I need to figure out x. And so here's how I calculated h, because this h is the leg of this right triangle over here, where the other leg is 1/2 of the square root of a squared plus b squared, and the hypotenuse is x. So h squared plus this quantity squared equals the hypotenuse squared. And then I just have to do some algebra, so I can simplify this down. And the square here undoes the radical in the numerator and squares the denominator, 2, which becomes 4. And the value x, which we found a moment before, is still a squared plus b squared over 2a, so I've got to square that. And then, continuing down, just a little more algebra. So I've moved this quantity over to the right. So if I subtract a squared plus b squared over 4 from both sides, then I can solve for h squared, and it's this quantity, which I squared out here, minus this quantity, which was brought over to the right here. Now when I square this quantity, it becomes a to the 4th plus 2a squared b squared plus b to the 4th, and the denominator becomes 4a squared. And then when I brought this to this side, we have this, and I want to combine these two fractions together, so I need a common denominator in order to do that. And so I multiplied this quantity by a squared over a squared to get a common denominator of 4a squared in each case. And now I can combine these two together, and I could subtract this fraction from that fraction in this way, and the numerator becomes a to the 4th plus 2a squared b squared plus b to the 4th, and then minus this quantity, which is going to be minus a to the 4th minus a squared b squared. And some simplifying happens in this numerator here, because the a to the 4th gets canceled, like this, and 2a squared b squared minus a squared b squared is just 1a squared b squared, and then all I have left is plus b to the 4th. And so I see that h squared is equal to this quantity, and I can now factor out b squared from the numerator, and so that's a squared plus b squared when the b squared gets factored out over my denominator of 4a squared. And so it's very easy to solve for h from this by taking the square root of both sides, because the square root of b squared is b, and the square root of 4a squared is 2a, and this becomes the square root of a squared plus b squared. And I found h. And so my area is this quantity here, and so when I take my h and multiply by 1/2 square root of a squared plus b squared, I get the same answer as before. b over 4a times the quantity a squared plus b squared. So same answer as before. Now comparing these two solutions, this alternative solution, which is much longer than the original solution that we chose because that was more optimal, and comparing these two solutions gives a nice illustration of how well it pays to consider all of your options first before solving a problem, so you can strategize as to the optimal method that you want to use to solve your problem. And you'll find that in mathematics, looking at a problem from a different angle or changing your method of solving can change a difficult problem into an easier problem. And this is something that all mathematicians need to keep in mind when researching and solving problems.